Hello everyone, this is Neeraj Kumar Gaud, BCA Department, IIMT College of Management. Today, I'm going to give an online lecture on relation and function. Let's start. Relation. A relation R from a set X to a set Y is defined as a subset of the Cartesian product X cross Y. We can also write it as R subset of X comma Y belongs to X cross Y such that X is related to Y. Now, if we have A which containing two elements 1, 2, then the Cartesian product will be 1, 1, 1, 2, 2, 1, 2, 2. And as we know that relation is nothing but it is a subset of the Cartesian product. So we have selected some subset of Cartesian product A cross A. So my first relation will be empty relation. R2 will be 1, 1. R3 will be 2, 2. R4 will be 1, 2. R5 will be 2, 1. R6 will be 1, 1, 1, 2. R7 will be 1, 1, 1, 2, 2, 1. And R8 will be 1, 1, 1, 2, 2, 1, and 2, 2. Next is types of relations. So different types of relation are follow. Number one is anti-relation. Number two is universal relation. Number three is identity relation. Number four is inverse relation. Number five is reflexive relation. Number six is irreflexive relation. Number seven is symmetric relation. Number eight is anti-symmetric relation. And number nine is transitive relation. So first is anti-relation. When there is no element of set X is related or mapped to any element of X, then the relation R in A is an empty relation and also called the void relation. That is R equal to phi. For example, if there are 100 mango in the food basket, there is no possibility of finding a relation R of getting any apple in the basket. So R is void as it has 100 mango and no apple. And this diagram representation of empty relation. Next is universal relation. R is a relation in set A and we call A is a universal relation if and only if every element of A is related to every element of A. That is R is equal to A cross A. Next is identity relation. If every element of set A is related to itself only, it is called identity relation. That is I equal to A comma A belongs to A. For example, when we throw a dice, the total number of possible outcome is 36. That is 1, 1, 1, 2, 1, 3, and so on 1, 6. Also 2, 1, 2, 2, 2, 3, and so on 2, 6. Similarly, 3, 1, 3, 2, 3, 3, and so on 3, 6. Likewise, we get 6, 1, 6, 2, and so on 6, 6. From this, if we consider the relations 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, it is an identity relation. Inverse relation. If R is a relation from set A to set B, that is R which belongs to A cross B, then the inverse relation will be B comma A such that A comma B belongs to R. Likewise, if we have this is relation A comma B, the inverse relation will be B comma A, which is mirror image of line Y is equal to X. Now we can take another example. For example, if you throw two dice, if R is 1, 2, 2, 3, then R inverse will be 2, 1, 3, 2. Here the domain is the range of R inverse and vice versa. Now, reflexive relation. A relation is a reflexive relation if and only if every element of set A is mapped to itself. That is, for every A belongs to A comma A belongs to R. For reflexive, we consider an example. Suppose we have set A which consisting of 5 elements with this relation. That is, if every node has a loop, a relation is reflexive. Likewise, like 1 has a loop, at node 2 has a loop, node 3 has a loop, node 4 has a loop, similarly node 5 has a loop. So this diagram represents a reflexive relation. Take another example. Suppose let L be the set of all lines in xy plane and R be the relation in N defined as R, which is L1 comma L2. L1 is parallel to L2. Now we are going to show R is reflexive. So solution, since every line is parallel to itself, that is L1 is parallel to L1, this implies L1 comma L1 belongs to R. This implies R is reflexive. Irreflexive relation. A relation R on set A is said to be irreflexive if A comma A doesn't belongs to R for every A belongs to A. That is this diagram representation of irreflexive relation. That is A doesn't form any loop, B doesn't form any loop, C doesn't form any loop, as well as D doesn't form any. Let's take another example. Let we have A which is consisting 1, 2, 3. And we're defining two relations, R1 and R2. R1 is 1, 2, 2, 2, 3, 1, 1, 3. R2 is 1, 2, 2, 1, 3, 1, and 1, 3. Is the relation R1 R2 irreflexive? That is clear from R1 that 2 which forms a loop, that is 2, 2, hence this is not irreflexive relation. Whereas R2, no element forms a loop itself, this implies R2 is irreflexive relation. Next is symmetric relation. A relation R defined on a set A is said to be symmetric if x comma y belongs to R implies y comma x belongs to R for all x comma y belongs to A. Or when x is related to y implies y must related to x for all x comma y belongs to R. So with this diagram, we can also show that this diagram is symmetric. That is, A is related to B and also there is a B is related to A. Here, B has a path from B to C. Similarly, C has a path from C to B. Similarly, C has a path from C to D and also D has path from D to C. This implies this diagram is symmetric relation. Now take another example. Let L be the set of all lines in xy plane and R be the relation in L defined as R is L1 comma L2 such that L1 is parallel to L2. Now we are going to show that R is symmetric. Since from this diagram it is clear that line L1 is parallel to L2, so we can also say that L2 is parallel to L1. This implies L2 comma L1 belongs to R. This implies R is symmetric. Now antisymmetric relation. A relation R on a set A is antisymmetric if and only if A comma B belongs to R and B comma A belongs to R, then A equal to B. For example, let we have A which consisting 1, 2, 3 and we're defining relation R 1, 1, 2, 2. So we are going to show this relation is antisymmetric. So this relation is antisymmetric because as A is equal to B when A comma B and B comma A both belongs to R. Next is transitive relation. A relation R defined on a set A is said to be transitive if x comma y belongs to R, y comma z belongs to R. This implies x comma z belongs to R for all x comma y comma z belongs to A. Or when x is related to y is related to z, then we are going to show that x is related to z or not. If x is related to z, then we show that, then we can say that this relation is transitive relation. From this diagram, we can easily show that A is related to C and C is related to D. And also there is a path from A to D. This implies this diagram is transitive relation. Also, B is related to C and C is related to D. And also B is related to D. We can show that this relation is transitive relation. Also, that we have discussed previous example, we are going to show that this relation is transitive. We can easily show that line L1 is parallel to L2 and L2 is parallel to L3. We can easily show that L1 is parallel to L3. This implies L1, L3 belongs to R. This implies R is transitive. Now next is equivalence relation. A relation R defined on a set A is said to be an equivalence relation if R is reflexive, symmetric, and transitive. So let's take an example. Let L be the set of all lines in xy plane and R be the relation in L defined as R L1, L2 such that L1 is parallel to L2. We show this relation equivalence. As we already discussed, this relation is reflexive as well as symmetric as well as transitive. Hence, this relation is equivalence relation. Pick another example. Let we have A is consisting 1, 2, 3, 4 R, which is a relation we define 1, 1, 1, 3, 2, 2, 2, 4, 3, 1, 3, 3, 4, 2, and 4, 1. We're going to show that R is equivalence relation. So first we are going to show R is reflexive. The relation R is reflexive as 1, 1, 2, 2, 3, 3, and 4, 4 belongs to R. Symmetric. The relation R is symmetric because whenever A, B belongs to R, B, A also belongs to R. Example, 2, 4 belongs to R implies 4, 2 which also belongs to R. Transitive. The relation R is transitive because whenever A, B and B, C belongs to R, we're going to check either A, C belongs to R or not. Clearly, 3, 1 and 1, 3 belongs to R and also 3, 3 belongs to R. So R is reflexive, symmetric, and transitive. Hence, R is an equivalence relation. Now, the next topic is functions. It is a mapping in which every element of set A is uniquely associated at the element with set B. The set of A is called domain of function and set of B is called the codomain of function. Now, domain of a function. Let f be a function from A to B. The set A is called domain of function. Now, codomain of function. Let f be a function from A to B. The set B is called codomain of function. Last is range of function. The range of a function is the set of picture of its domain. In other words, we can say that it is a subset of its codomain and is denoted as f domain. So it is clear from the picture that this is your domain and this whole is your codomain and the image of domain will be your range. Now the types of function. Types of function are generally classified into 4 different types. That is based on element, based on equation, based on range, and the based on domain. Based on element, we have 6 types of function: one function, many-one function, onto function, one and onto function, into function, and constant function. Based on equation, we have 5 types of function: identity function, linear function, quadratic function, cubic function, and polynomial function. Based on range, we have 8 types of function: modulus function, rational function, signum function, even and odd function, periodic functions, greatest integer functions, inverse functions, and composite function. Based on domain, we have 3 types of function: algebraic function, trigonometric functions, and logarithmic functions. So type of function based on element, the number is 1-to-1 function. A mathematical function is said to be 1-to-1 function if every component of the domain function possesses its own and unique component in the range of the function. That is, we can also say that every element of domain must have unique and distinct image in the domain. Now, check whether the function from natural number to natural number is 1 to 1 or not. We have defined a function f of x is 3x minus 2. In order to check the function is 1, 1 or not, we have to consider an algorithm. Like we have to take f of x1 is equal to f of x2. On solving, if we get x1 is equal to x2, then we can say that our function is 1, 1. So what we have to consider f of x1, which will be 3x1 minus 2. F of x2 will be 3x2 minus 2. So after cancelling minus 2 both sides, we left with 3x1 is equal to 3x2. After cancelling 3 from both sides, we left with x1 is equal to x2. Hence, our function is 1. Many-one function. A function f is many-one function if two or more different elements in x have the same image in y. That is, it is clear from the picture that A and B have same image 1. Similarly, C and D have same image 3. So this diagram representing a many-one function. Onto function. A function is onto function if two or more components in its domain have the same component in its range. Also, we can say that every element of codomain must have image that is called pre-image in domain. Let's take an example. If fx is equal to 2x plus 1, which is defining from set of real number to real number, we are going to check either this function is onto or not. For checking the function is onto or not, let's first put the function fx equal to y. That is f of x equal to y. So we will get y is equal to 2x plus 1. We shifted 1 from right hand side to left hand side, we get y minus 1 is 2x. So now after solving, we get x is equal to y minus 1 upon 2. Now to put the value of x in the function, we get f of y minus 1 upon 2 will become 2 times of y minus 1 upon 2 plus 1. Taking LCM 2, we get 2 times of y minus 1 plus 2 upon 2. After solving this, we comes up with y. Since we get back y after putting the value of x in the function, hence the given function is onto function. Now bijection function. A function f from a to b is bijection if it is 1, 1 as well as on. In other words, a function from a to b is bijection if it is 1, 1 and on 2. So if a is equal to r minus 3 and b is r minus 1, considering a function from a to b defining as f of x is equal to x minus 2 upon x minus 3, we are going to show this function is bijective. So to show the function is bijective, we first prove this function is 1, 1. Then we prove this function is on. So for 1, 1, let x1, x2 belongs to A and such that f of x1 is equal to f of x2. Then we will get x1 minus 2 upon x1 minus 3 equal to x2 minus 2 upon x2 minus 3. On cross multiply, we get x1 minus 2, x2 minus 3 equal to x2 minus 2, x1 minus 3. On multiplying, we get x1, x2 minus 3 times of x1 minus 2 times of x2 plus 6. Similar manner, x1, x2 minus 3 times of x2 minus 2 times of x1 plus 6. So after cancelling x1, x1, 6 from both sides, we left with 3 times of x1 minus 2 times of x2 equal to minus 3 times of x2 minus 2 times of x1. Take the right hand side to the left hand side. It comes out with b 3 minus 3 we taking common out, we get x1 minus x2 plus 2 we get common out, we get x1 minus x2 is equal to 0. On subtracting, we get minus times of x1 minus x2 equal to 0. We get x1 minus x2 is equal to 0. This implies x1 is equal to x2. So this implies our given function is 1, 1. For onto, let y belongs to b, r minus 1 be an arbitrary element. Then we consider f(x) equal to y. This implies x minus 2 upon x minus 3 is equal to y. This implies x minus 2. On cross multiply, it comes out x minus 2 is equal to x minus y minus 3y. We shift xy to the left hand side, we get x minus xy equal to 2 minus 3y. Taking x common, we get 1 minus y equal to 2 minus 3y. Now we get the value of x will be 2 minus 3y upon 1 minus y, or the value of x will be 3y minus 2 upon y minus 1. Now they put the value of x in the function, and after putting this, after solving this, we get it by. Hence fx is onto. Hence we have proved both 1, 1 and onto. This implies the given function is bijective. Now into function. A function is said to be into function in which there is no element of codomain, in which there is an element of codomain y and does not have pre-image in domain x. So it is clear that this is a codomain, have element 4, which does not have a pre-image in domain. So this implies this function is into function. Next is constant function. A constant function is one of the important form of a many-to-one function. In this domain of every element has single image. The constant function is in the form of fx equal to c, where c is real. So this diagram representing a constant function. Types of function based on equation, we have identity function, the function that has same domain and range. Constant function, the polynomial function of degree 0. Linear function, the polynomial function of degree 1. Quadratic function, the polynomial function of degree 2. Cubic function, the polynomial function of degree 3. Types of function based on range. Number 1 is called modulus function. The modulus function is the types of function that gives the absolute value of the function irrespective of the sign of the input domain value. The modulus function is defined as fx equal to mod x. So it is clear that the value of x of minus 2 will be 2. The value of 2 will be 2. So this diagram representing a modulus function. The value at 2 is 2. The value at minus 2 is 2. Rational function. A rational function is the type of function that is composed of two functions and expressed is in the form of fraction x. A rational function is the form of fx upon gx, and gx is not equal to 0. So here the example of rational function of fx equal to 1 upon x rectangular function. Next is signal function. The signal function is the type of function that helps to know the sign of the function and does not give the numeric value or any other value for the rates. Next is periodic function. The function is said to be a periodic function if the same range appears for different domain value in a sequential manner. Next is inverse function. The inverse of a function is the type of function in which the domain and the range of given function is treated as the range and the domain of the inverse function. The inverse function fx denoted by f inverse, but not inverse function exists if a given function is bijective. That is, if a given function is 1, 1 and onto, then we can find out inverse. Otherwise, we can't. Greatest integer function. The greatest integer function is the type of function that rounds up the number to the nearest integer less than or equal to the given number. The greatest integer function is represented at fx is this. For example, if we want to find out the value of 0.5, the nearest integer is 0. And we're going to find out 1.7, the nearest integer is 1. So this diagram representing a greatest integer function. Composite function. The composite function is a type of function that is made up of two functions that have the range of one function forming the domain of the another function. So let's take an example. Let we have set x which consists in 1, 2, 3. We have y which consists in 1 and a and b. We have z which consists 5, 6, 7. So we're defining a function that 1a, 2a, 3b, and we're defining a function a5 and b7. Now we're going to find out composition of GOF. So we're going to find out GOF of 1, which will become g of f of 1. So we have f of 1 is a, it will comes with g of a. Now what value of g of a? G of a value is 5. Similarly, value GOF of 2, this will become g of f of 2, and f of 2 is a. Now the g of a is 5. Similarly, GOF of 3, which is g of f of 3, f of 3 is b, and g of b is 7. Now the type of function based on the algebraic function. An algebraic function is the type of function that is helpful to define the various operations of algebra. This function has a variable, coefficient, constant term, and various arithmetic operators such as addition, subtraction, multiplication, and division. Trigonometric function. The trigonometric function is a type of function that has a domain and range similar to any other function. The 6 trigonometric functions are sine theta, tan theta, cos theta, secant theta, and cosec theta. Now is logarithmic function. Logarithmic functions are the type of function that is derived from the exponential function. The logarithmic functions are considered to be the inverse of exponential function. So this is diagram of logarithmic function. Thank you.